we're going to begin. Well, thank you very much, everyone, for coming. I'm delighted to introduce Dr. Yuan from Glasgow University, School of Computing Science. I wanted to make sure that I get it right. And also Institute of Cancer Sciences at Glasgow University. Kay is very experienced, recently completely focused on computational pathology, done a lot of interesting work that he's going to tell us about on learning representations of histology images, and has got some really great ideas about where the future of the field might lie. So I'm really excited about this talk. And I think without further ado, I'm just going to hand it over to Kay to tell us all about the exciting things that he's been working on.
Thank you very much, Nathan. Thank you very much for inviting me. I'm very privileged for this great opportunity to share with you my ideas and my work regarding learning the how do we do tissue representation learning for pathology images. So before I start, I wanted to maybe bring a little bit of background for you to better understand where my ideas came from, how I go about to approach problems. So. Okay, so before computational pathology, most of my works is focused on cancer evolution using genomic data. So I'm very much interested in understanding cancer from an evolutionary perspective. So in that aspect of the work, so our understanding around cancer is that cancer is a evolutionary process. But the way we understand this evolutionary process is to assume that there is a timeline going on at the beginning of the timeline. So there's some mutation happens to the tumor, and then that start off the growth of the lesion. And then over time, the tumors start to accumulate all kinds of different mutations at various different time points. So at the time point where the tumor got sampled, got taken out by the clinician, then we will see a interesting diversity of genetic events within the tumor. So, but from traditional evolutionists, mostly studied on the phenotypic side. So this is Darwin's famous Darwin's 4 different finches, where he started out by noticing the diversity in the phenotype of the birds. We can see the beaks are different, the size of the beaks are different, and their other facial features are different. So been focusing on cancer genomics and understanding evolution from a genomic perspective so much, we kind of lost our perspective on the phenotypic side. So here are the two different examples of tumor images, where you see there are noticeable differences in them, but are they different in the way that we can compare? So we can quantify. Okay, this is the beak of the tumor different, and then without doing so, what I'm feared is that we won't be able to appreciate how different the phenotype or the morphology between tumor really is, and start to appreciate the information that gave rise to those things. So interestingly, that I think a lot of the emergence of deep learning technology has made us very ambitious in trying to understand the molecular underpinning of pathology images. For example, about 2 years ago, there were 2 concurrent studies published in Nature Cancer. So what I did is to try to predict all kinds of mutations across all different cancer types, just from information that can get from a standard diagnosis slide. There's subtle difference. One from FFPE, a technical clinical setting, and the other one is from a fresh frozen samples. But the setup is very much the same. You have a whole slide image. You have one label attached to it. That label in this case will be whether the patient has the mutation or not. And they have various level of success in predicting different mutations. But what I wanted to cautious about this approach is the how much information or how much story there is about that label, meaning whether we know there's a mutation exists in the patient. So this is a study published last year about intra-tumor heterogeneity on the genetic, on a variety of different genetic alterations. What I'm showing you here are two plots about the level of diversity in ISMV. This is point mutation, the same information, the same label as previous two studies were trying to use to predict. So the second one is called structural variants. So these are the mutations that are involving, that are more structural, involving more genetic materials. So they're potentially should have more serious consequences. So the signal that you're seeing here are a fraction of subclonal events. So what it means is that so each point you see is a sample, and that number tells you in this category, for example, if you're looking at some of these, in that sense, so for all of the mutations identified in this tumor, you could estimate how the percentage of cancer cell carrying that very mutation. And then this percentage telling you that what fraction of those mutations are estimated to be subclonal, meaning that only a fraction of cancer cells carry it. And you can see that the striking first message of these two figures is that there's a great deal of diversity in them. So for every single cancer type, for all the mutations that we able to detect in those tumors, we see very variety of different level of subclonal events. So what it means for us, we're trying to predict mutation from images. It means that in the worst case scenario, when you know that this image, this patient with the image has a mutation being positive label 1, in the worst case scenario, it could be that none of the cells in that image carry that mutation, because that mutation may be detected as a subclonal mutation, only exists in a subpopulation of the cancer cell that happen to be not in the image that you saw. So this generates huge problem with us. Of course, that all boils down to our traditional argument of cautious about end-to-end learning of the quality of the label. Not only the label are very expensive to collect, but once you're able to collect them, you have to be very careful about how to use them in relation to your predicted task. And then in addition to this, there's various challenges in making predictions, how to interpret the prediction. I will show some example of how that really dictate of us choosing one over choosing a certain technique pathways. And also, you will always be vulnerable to noise. We're talking about noise due to the fact that image being produced by different centers, and interesting noise like the one that I've just
hear the voice.
Sorry?
I'm not able to hear the voice. Is there any problem? Hi. Can you hear me?
Yeah.
Yeah, I can hear you now. Thank you.
Okay.
Clicking on that cross up there. Which cross? In the middle. Yeah. Okay.
Am I audible now? Okay. So that's really, in my view, summarize boils down to these three major challenges. So the rest of the talk will be our own perspective on how do we tackle these issues. And so generally the approach that we do is to not conditioning our deep learning framework upon a given label. So that's why we opt for looking at a variety of different deep representation learning approaches for pathology images. Actually, I want to acknowledge that it's the joint work between my group in Glasgow and with Rod Smith and John LeCun. Most of the work is done led by Alberto Cleodo, and we got help from Aris group from New York University. So today I want to talk about two types of representation learning approach. So the way I see it, they differ by the general strategy of constructing representations. So the first one is learning by synthesizing. So will be the typical deep generative models. And the second one is learning by perturbation, meaning that you tweak your data, augment data, and then you build a model such that you can recognize those perturbations. But interestingly, that these two principles are not that novel in science. In biology, we have very similar things that you're trying to create a system, whether using model system or using cell lines. And in functional genomics, you try to perturb the genome such that you understand what the consequence of it. So I just want to strike out that interesting parallel with AI and what has already happened in science for forever. Okay, so the first approach that we want to talk about is called pathology again. So this is again, as I'm sure I don't need to introduce Guy to this audience. Guy is a very famous deep generation model and is featured by its capability of generating very sharp, high quality images. So it fits very well with the learning by synthesizing principle. So when we started, our goal is, our intuition is that, okay, again, is if we are able to build again that can generate very realistic images, it must be that the network or the model is capable of learning something very useful from the image itself. So this is the architecture we adopt. Essentially, it has three key components. So first one is the main architecture, that is a big GAN model. Again, that is a very state of the art around 2018. That has been shown to be able to generate a fairly large images with high quality. The other key components of the model is this access to a latent space. That comes from what is known as a style GAN architecture, which they introduce a style normal transformation that will give you access to a latent space, which means that every single image that you generate has a latent space associated with it, a vector of latent space in the latent space also with it. So that will be our target domain of extracting useful representations. And the rest of it is relative standard. We have a technical difference in the laws of the model that we will get to in the future in a few minutes. So here you see the general quality of the image that is generated. So without telling you which one is real, which one is fake, so myself find it very difficult to distinguish real from fake ones. So here you see images trained, model producing images trained from two different cancer types. On top, you see these are actually breast cancer images, and at the bottom, these two rows are colorectal cancer images. So at this point, we're fairly convinced. Of course, you can also assess the FID metrics to have a quantitative measure of how actual quality of the data. So, but the point is that we're happy that we are able to generate good enough image. Yes.
Back to a couple of slides back. Yeah, and ask a quick question.
Yeah.
At a very high level, you talk about learning by synthesizing from the latent space. Whatever goes into the latent space, that representation is reflective of whatever has gone into the network, right? Yeah. Into the generator, the mapping network, and then into the generator network, and then into the discriminator. It's all whatever it's seen, right? Yeah. So whatever you're able to then generate or synthesize from that space is still reflective of the distribution of the images that it has seen.
Yeah.
Right.
Yeah. That's
So,
correct.
so what new are we expected to learn from here?
I think the goal is not necessarily to learn new things. It's more about have a general representation of the image distribution of the image. Right? So if that representation does not rely on any label, so that's our goal for this entire set. So without any label, and if once you're able to do that, and you examine this latent space in detail and see how much useful information is there. So that's the intuition.
Okay.
So here I just want to point out a technical detail for the GAN is that is the loss that we use is a slightly different version than the Hinge loss that is mostly used. Our experience is that with this relativistic average discriminator, so what happens? The training become much more smoother. Here I'm showing you two examples on your left. This one is the image generated by the GAN with this loss, and this is the image generated without it. I hope you can appreciate that this one looks a lot more blurry. Unfortunately, we don't have any scientific reason why this is happening, but this is what we observe in our experiments. Okay, so now let's take a look at the latent space about those images. What we see is that this is an example of images tails from a colorectal cancer data set. So here you see that each of the dots in this UMAP representation, these are UMAP reduced dimension of the original feature space. They are color coded by their tissue type. And you can see that there are certain structures exist in this latent space. And if you pull out what the corresponding generated image of those points are, they more or less match what we think they are in terms of tissue type. But you see some weird things going on. But I think this is the limitation of the training. But by and large, there seems to be a meaningful structure in the latent space. And so we take a look at, okay, what are the effect of those setups in the GAN that gave rise to this? Because when the setup, we didn't expect to see this. We did nothing artificially to impose this to happen in the latent space. So what we did is try essentially taking out various components of the model to see what's happening. It turns out the style transformation is the key. And so here you're seeing, I know the resolution is terrible. You won't be able to see the finest. You don't need to worry about that. The take-home message from this figure is that on the top, you see the one with style transformation, and then they are highlighted with different tissue types. Then you can see that a bunch of points are grouped together, and a part of the space is blank. So this is where only a subtype of the tissue type is highlighted. On the bottom of this group of figure, you see again without style transformation. And then we did the same thing again, highlighting all of those points with specific tissue type. There you see the structure is not that clear. Yes?
As what is the dimensionality of this latent space? How many dimensions did the images were the images reduced to?
So these, the original, if I remember correctly, I think it's around 1024. This is UMAP, just two-dimensional representation.
So what transformation was used for the ones at the top? Ones at the top have gone through some transformation.
Oh, the style GAN transformation.
Oh, the style.
So that the bottom one is the one without. Again, you can also, we do the same thing as everybody would do for a deep generative model. We do linear interpolation. Again, something interesting that we observe is that usually you expect to see a gradual change in the image. For example, a cell maybe gradually start to appear as you're changing through the latent space. we basically see less of that smooth change in our latent space. What we see is that the appearance of certain cells is more drastic compared to, we test the same thing with VNE, which is clearly a smooth emergent. We feel that, okay, this, although it's strange, but it actually fits the reality better, right? If you assume your linear interpolation is somehow represent a progression of a disease, you don't see a cell drastically, sorry, a cell smoothly start to appear in the middle of the image. They always drastically move into this area. So that's another interesting observation that we find. And
a question on that previous slide. So if you think about it from manifold learning point of view, this is, do you see that this might be a sub-manifold that you're trying to traverse on? Because if you're not, if there is a sub-manifold and you're not traversing on the sub-manifold, you might be going completely off it. Because if you're just above or just below the manifold, you may be reconstructing something completely different. Whereas if you stay on the manifold, you will probably then likely see some kind of linear transformation or gradual changes from one part of the manifold to another part of the manifold.
That's totally possible, I think. So here, as you can see, the UMAP projection of the corresponding points in this interpolation, but we could very well see a partial view of that. It's actually not a perfect linear interpolation would be actually smooth in this case. So now we're now to do very elementary arithmetics on the latent space. And then this again come as a surprise to us that we basically saw some meaningful semantic information basically encoded in those basic operations. For example, you see here's the benign tissue plus cancer cells, and if you take away a vector that corresponds to primarily tumor cells, the result that you get is pretty much the image without tumor cells. And now so this one that we see in the breast cancer data set, and similar thing we'll observe in the colon, where is this example where you add adipose tissue plus lymphocytes, and then you end up with something. I doubt this is actually real. That you will actually be able to see in the real images, but nevertheless, what you get is a combination of adipose like structure with some lymphocyte-looking dots in it. So we think that okay, the latent space seems to be interesting.
How do you perform these geometric operations, these kind of basic arithmetic operations? In fact, it's not even geometric operations. How do you perform these arithmetic operations in the latent space? You just actually do the plus and minus of the latent space coordinates?
Yes, exactly. In this with this 1000 dimensional vector, and then you get the result. You attach the generator to it.
Is there any trick, like you do some kind of normalization?
No, I don't believe we did that.
Okay, so just arithmetic of the latent space coordinates.
Yeah, exactly. So that's why it came to us as a surprise.
Quite amazing.
Just a quick question. So if we really, the generative model has learned the coherences of different types of cells, then let's say if I reduce the cancer cell in a normal image, a normal tissue should also be accompanied by immune cells automatically. Do you see any sort of that trend?
No. I think I should emphasize that it's not all of the operation that you do will end up something beautiful like this. There is certainly
best example.
Yeah, there's certainly a cherry picking happening here. But I think that's a very interesting thing to look into. We haven't done enough to actually appreciate that, whether that's happening or not. But I guess the point is that the upper bound of this is very promising, that there is a hope of actually encoding semantic information there in the latent space. I think that really illustrates the potential of learning things without label.
What is the architecture of the mapping network like?
So that I need to get back to you.
Okay.
Yeah,
It seems magical that it can transform into latent space where you can perform arithmetic operations like that.
So we have a standard journal publication of that. I believe that the detail of that architecture is in the.
Okay.
So all of those are good and interesting, but those findings are basically based on fake data. So what we do is that we really wanted to use this network to be able to explain real data. So what we did for Pathology and Plus is to essentially just add an encoder to ask to allow the training essentially to give us an encoder to project real images back to this latent space so that we can make assessment about real images. There's nothing too fancy here. This will not really change how the generator and discriminator and the mapping network are changed if you do that. So the work of the result of this published recently. So again, we very pleased that the structure of the latent space is very much preserved. So here you see breast cancer images and their projections in the UMAP space. So they are color coded by the density of cancer cells. So because you can generate fake images, so these are real images. You can count the cancer cells in each one. By the way, we did the same thing with our fake images, and we find by and large the distribution of cancer cell counts is the same.
How do you count?
So you just you do segmentation and call cancer cells, and then just number of cancer cells per town. And then what you see that there seems to be a difference between large number of cancer cells in the image and smaller number of cancer cells in the stain. And similar thing happens with tissue type of colon cancer. So these are all real images. Some of the projections might be less meaningful. These are clear just background and some attributes. And you have tumor area and the stroma, etc. So that's the projection, but you can assess this latent space quantitatively by putting a linear classifier head on it. So that's exactly what we did. So we ask a logistic regression classifier to predict individual tissue types, and then we find across the board seems to be performing fairly well. So that take-home message is that structure is predictive enough about tissue. So that's where we are about the generative model. Yes.
Just a question. So if you hadn't generated the latent representation from a generative model, that's the way you are, and you use any dimensionality reduction technique, would that arithmetic still be there?
That's a good question. I think that can certainly be tested. We haven't done that. It really depends on the. So you're suggesting that you do a UMAP and reduce the raw pixels even. Would you see
the ResNet features and then UMAP of that?
Yeah, we haven't done that specifically, but we've done other type of benchmarkings with pre-trained models features. But that's not didn't come up. Yes.
Salman, I have two questions. So first is suppose any image, consider the case of image to image translation model or any unit model. So there is commonly there is a practice to use skip connections in the generator. So suppose from mask to image we are converting.
Okay.
And using the say pix to pix model, image to image translation.
Mm-hmm.
So they generally use skip connections. So if those skip connections are there, what do you think which latent space to be considered for these arithmetic operations or to capture the meaningful features?
Wow. I'm not sure. I guess we never tested that kind of network before. I don't think I have the intuition of what the result of that will be.
Okay, and second question also, how do you compute the Fisher insertion distance? This, I read that in paper.
Yeah.
So how do you, I mean, exactly, is that by the original definition of retrieving it on imaginary data set and computing the distance between pixel maps? Is that still applied?
The same applied. We did that. We also did computing FID based on feature that you extract traditionally using traditional CV approaches, all kinds of gray level features, and then we use CR image, 1 divided by Yuan. We also use that the cell count as another one. So whatever that feature set you get, you can basically attach an FID on that and compare with a single number. So we did that. So generally, we see the same trend there.
I have a question.
Yeah.
So if you go back to the slide that you added two presentations together, can you go back?
This one?
A little bit more. Yeah, this one.
Okay.
So is it possible for us to subtract presentation? So yeah, for example, consider that we have in the picture number B, and then we have the middle picture with it densely with epithelial, and then we subtract that presentation with one with like densely lymphocyte. So what will be the outcome of that?
So if you don't have that in the original image, that's a good question. I don't know.
Okay.
You might end up with something clearly nonsensical, or you actually, I think ultimately it depends on the manifold of the latent space that you operate.
Yeah, so another thing I want to ask is that because from this demonstration, assume that you can add it and it results into something meaningful. What does it say about the separation of the manifold? How much actually the meaningful content decoupled from this model? So for example, we have trauma center, and then we have lymphocyte center, and then epithelial isolate like that. And how does it say, how do your latent space say about their separation? Can you accept that?
Yeah. In this particular case, we don't have that for breast cancer, but the cancer cell count, in a way, approximate that. You have less cancer cell count. Potentially, we didn't have the numbers for lymphocytes. We'll have. So in the second half of my talk, I will show some results. Similarly, you might be wondering whether why I didn't use HoverNet to get the cells. I will have answer for that later. But using a colon cancer as an example, you see so drastically different morphology seems to be still separated in this latent space.
I'm just thinking, is there kind of limit on what kind of operations and between what kind of tissue type? Because you can immediately start thinking about all kinds of operations between these 9 tissue types.
Exactly.
Plus, minus, and multiply. And,
yeah, you can do deconvolution and create new.
What's the essence of this all? What is the latent space actually capturing? And
I think that's actually the reason that we didn't go too deep into this. So
But I think that's exactly the reason why you should go deep into it, because it's fascinating.
Yeah, I totally agree. I think the reason that we didn't go deep into this is that we are worried that we get this for free. We didn't impose any structure on the latent space, and then you get this. And we were really worried about this is just an artifact.
I mean, are there some kind of inherent dimensions to this? If there is a manifold in there, are there some dimensions that go from one end to the other end, benign to malignant, and the other dimension is it goes from low lymphocytic density to high lymphocytic density, and the other dimension is something to do with necrosis or whatever. Are there any biologically related dimensions here that could be manipulated? Because that would make it really, really interesting.
Yes. I think that's I agree. That's very fascinating. I think so in our discussion, we thought that we are only comfortable in assessing that if we actually impose that or encourage that in the model construction. So I think at this stage, with the model architecture, without those specific setup, we thought, okay, we just get lucky here. And there's a real question about whether this is actually generalizable, or just it could be an artifact of the training data that we use there. But I totally agree that I think there's already interesting work around VAE, not particularly again emerging, especially in the protein sequencing domain, where you can actually impose very effectively about structures in the latent space, and then start to look at where they can decouple this information. So to switch the gear a little bit, I want to talk about not about if you forgo the capability of generating image, and then you essentially, in my view, you reduce the goalpost a little closer to you a little bit. The goal will be recognizing perturbation. Again, this is a very dynamic field. Recently, there are lots of methods from this, all known as self-supervised learning approach. The general scheme of things is that you do data argumentation of various kind, and then you ask in this case two networks structure to one for the in this case two batch of different argumentations, and then you get the representations, and then whether you can do contrast learning, or in this case we opt for the Barlow twins approach. The principle of this approach is actually quite intuitive. So your loss is just that you're trying to minimize the invariance, right? And then plus the cross correlation between those perturbed representations. So the hope here is that you're actually able to look through those artificially induced changes to the images. They will be manifest themselves in the cross correlation between representations of the meaningful information in the image will repeat itself to a certain degree, and you'll be able to get it from here. That's Barlow twins. I find a very very intuitive model to understand. Of course, you can also try to use Sinclair other contrast approaches. We also tested that. We can show you some simple comparison. So, but the point is that I guess you can use any self-supervised learning network here to get some representation you get from the image. So our strategy is that you do the training, and once you settle down a network trained by self-supervised learning, and then you project all your tiles through that network. And the end of that network, you have your representation. So here, just the example where we did that for the TCAGA lung cancer cohort, where you see they're color coded by the two major different lung cancer types. So now I want to talk about what I see two strategies once you get those representations. So one strategy is recently very popular called multiple instance learning. So where you assuming that the whole slide image is a bag of examples, and they all share the same label. And then you can attack you can use the representations through a attention network to use ML to get a prediction. And the other strategy that we see is trying to find clusters in those representations. And then hopefully I can in a minute I can introduce how we see they are different and why we eventually opt for clustering rather than multiple instance learning. So here example of multiple instance learning results. So this is a task of distinguishing the two major lung cancer types. I believe the representation itself in this case are produced by Sinclair. So you can see very good AUC performance. And then if you look across different magnifications, it seems to be picking up the high weighted tails, meaning that tails with high attention weights, they seem to be looking at the correct phenotypes. So here you see stuff that seems to be matching adenocarcinoma patterns in the 20x magnification. And then we see similar patterns sort of preserved once you go higher and higher in altitude. But even there, with a selection of high-weighted tails, you can see these guys shouldn't be there at all, right? You start picking up things that you're not supposed to be picking up. So here's another example of multiple instance learning. So this time we use multiple instance learning and attach a survival learning model. So I don't want you don't need to worry about the details about the survival model. The take-home message of this is that you will be able to. So in this case, we're able to distinguish higher and lower risk very well, and this we think is a clear example for overfit to the data that we have. Again, if you look at the highly weighted tails in the latent space, you see some of them do capture meaningful patterns. So where in some places you see an intrastatic infiltration, but you start to see things that are a little bit weird. And also, again, this artifact seems to be very stubborn. So this really gave us, make us worry a little bit about going down the route of actually attaching ML to our representations and relying on ML to tell us what's important in the image and what's not important. And then there's also a logistic concern with that. Was ML, and then what you naturally want to use a threshold to only look at those you think to be highly attentive, high weighted ones?
Can I have a question?
Yes.
So can you tell us a little bit more about what MIL are you using for this discussion?
Okay.
Is it climb or is it something else?
We use a fairly standard MLs. So we use representation that we have, and then we feed it into a sigma type like layer. And you use that to compute the weight of each tail based on its representations.
So basically, a CNN that had been trained with the sigma function.
So could you repeat that question?
I mean, does that mean that you basically fit in the network, not the MIL first, but basically it's a threshold network, not the client, not the train family? Is it a standard convolutional neural network or is it a simple neural network to basically classify positive and negative with respect to your label? Is that what you mean?
No, we didn't use any architecture. So it's a transformation of your representations, and then the final prediction depends on the weighted sum of your transformations. Yes.
So was it the representation you learned by the methods you explained earlier, and then there was a retention layer connected to those?
Yeah.
I have just one follow-up question.
Yeah.
So you tried it on the method of this non-squamous cell carcinoma versus carcinoma, right?
Yeah.
If I remember correctly, those two look quite different from each other. Like I think adenocarcinoma has some flowering patterns, and the other one has a kind of haphazard structures.
Yeah.
So is it worth it, like in your experience and in your benchmarking experience, like what was your method compared to what was the simplest thing that you tried your method against? Like, do we want to imply the Barlow twins, or can something simple work in your experience?
So we've tested some pre-trained models, but we didn't do a large scale test on all pre-trained models on that question, because we expected to perform okay. So our collaborator from New York, they did a study in 2018. So I think they used Inception V3 network. They fully trained the network, and then they asked the same question. I think they get similar performance.
So your representation from CRC data set was like translated here. You used the representation you learned from CRC data set.
CRC.
The colon.
No. These are we didn't use any transformation transfer learning. We trained de novo from the lung cancer data set and get this.
So the question that comes to mind is, how would it compare to standard resonant features representation for the same patches?
Yes, I guess our goal is that we're not trying to establish a performance gain. I guess the point is that they achieve similar performance. I think for that, I think you see a 0.9 is, if I remember correctly, is pretty much the same as a Inception V3 results. It's only marginal statistical difference, non-significant differences.
I think your main goal here is to find out the problem with NIL, especially you can see that there are some artifacts getting very high rate. But I'm a little bit confused, maybe just find myself disconnected. We started with mutational clonality, and how did you transform all this learning from both approaches back to your original start, like different cancers, we see clonality proportionally different. So did you complete that experiment, or are we going to see those like that?
We are not there yet, but our hope is that we're close enough. Hopefully by the end of the talk, you also see it that way. So this is a LUAT, but I don't think these numbers are comparable. So we did benchmark TCGA LUAT overall survival performance. I think by and large we tested 40 different pre-trained models, around slightly below 0.6 C index is what you're looking for. These are highly inflated because they are overfit this data set. So the logistic problem that I want to talk about is that it's just you lose so much information in there, right? So back to your question, I set out to try to understand the diversity in the image. So here I'm only returning 5% or 10% of the image. I lose all that information. So this combined with those issues and challenges that we see with ML prompt us to go into the clustering direction. So here, this is the Barlow twins representation, and they're color coded by cancer type. and we did something that is very popular in the single cell literature, where I see they share the same problem with us. They all face high dimensional space with lots of points they're trying to do clustering. So we adopt their state-of-the-art approach. It's called latent clustering. And so this is the UMAP representation of that. If you have dots in there about, this is maybe just a partial view of what's happening in the latent space. Latent clustering algorithm is somewhat a community detection.
Hi,
yeah.
excuse me.
Yes.
What is the resolution parameter in this Leiden community detection method?
So they are, so they are tuned with a predictive task essentially.
So tuned on based on what? Do you have some validation data that, or I mean, you are tuning statistically?
No, actually, we actually tune it with a survival task, and then use that common set of clusters to look at all of our assessments. I don't have that data there, but yeah, shoot me an email. I can supply those information later, or we will have a preprint about this soon.
Okay, that's fine.
Okay, so if you look at the network based on those, they are color coded by their share of tiles that has those two different those labels indicating two different cancer types. And then you can see that those clusters do capture at least predictive information about cancer type. You can see that those orange-ish clusters on top, these are all LUAT examples. And as you're moving down in this direction, you start to see more and more fixed more and more mixed clusters. Okay. So now that this is an example where you can color code it, the original image with those clusters, and this is we see this as an example to show the robustness of clusters, because if your clusters are very much has lots of variability in it, you wouldn't see large stretch of area being clustered into the same label. So here we see that. So that's the confidence, give us confidence to moving on in the next step. So the next step what we did is that to turn the typo here. So we turn each whole slide image into a vector of cluster compositions. So here you see that this is a patient ID, their color. We have in this case 44 different clusters, and then the numbers just indicating their share of overall slide in the whole slide image. And then this actually gave us a handle to do a lot of associations with everything you have in the same data set. So this is the first thing. Again, we check out how are those composition vectors, how are they correlated with the question of the two cancer types. The rows represent different patients, and the columns of the schema represent all those different clusters. So here you see those concentrated clusters that are type specific. For example, these ones, they're all just with the orange one. And then not only they are type specific, some of them are also patient specific. So this again gave us hope that we may be able to capture patient specific information about morphology. So another good thing about having that vector is that you can produce something that is super duper interpretable. So this is a logistic regression fit of those cluster vectors. Then you can calculate the good old odds ratio for every single one of them. And then you find those clusters that give you the odds favor LUAT, and the odds favor the other type. You have all the uncertainty, you have p-values. It's very easy to communicate with your clinical biology biological collaborators. Yes.
Question number 3, for example, is differentially expressed, I would say, in this particular image, right? But still don't know what cluster 23 means.
Yeah, I will get to that.
I was going to ask.
Yeah. So now the first thing you can do is pull out those clusters that are deemed to be at higher risk or higher odds to be one over the other. You can take a look at the first thing we see is that there's a random sample of a large number of tiles from those clusters. So if you look at those tiles, our very subjective judgment at this point is that they are being clustered into the right group, right? And you don't see clearly all, for examples, in each one of those. So these cluster 28 and 16, they are all Luat cancer type. You do see these granular structures here and there. And if you look at those clusters that are deemed to be squamous cell carcinoma, you see that clearly lots of stroma-looking regions. And again, just do a random sample, you don't see clearly off examples. That means that you're really getting high-quality clusters. Yes.
I have a question. Have you tested on another independent cohort?
Yes, we did.
Okay. So is this result on the independent cohorts? Because so far I think you are doing on TCG.
So these clusters, these are on TCGA images. I will show you the independent
Because I'm interested in whether you have the plot in the next slide or the independent cohort.
Okay, I don't have that with you, but I have a predictive results based on that. So then you can, again, in the logistic regression, you have odds ratio. In the survival, you have hazard. Yes?
Our clusters are from all slides.
Yeah, they're from all slides. Yeah.
And why it's 44? Any other number could it be?
So
7, 10.
we, of course, yeah, there's a question of model selection. With latent clustering, there's a parameter. There was a question from the online audience. So you have to tune the parameter to get a configuration. So I think we cheat a little bit. So there we're not entirely unsupervised. We use a predictive task to help us to choose the parameter.
Hi, may I ask a quick question, please?
Yeah.
You didn't compute the label for the clusters, yeah? From the Leiden method. Am I right? Correct me, please, if I'm wrong. You are not computing the labels for each clusters.
No. I just use, what do you mean by computing the label of the clusters?
By that, I mean, for instance, these are tumor or lymphocytes or stroma. You are not computing any labels for the cluster. You are, okay.
No.
So do you have any information how there is a correlation between two clusters? There might be the possibilities that cluster number X and cluster number Y may be same. How can you ensure that?
That's possible, but if they are, we thought that kind of information will manifest itself in our cluster composition labels. Composition vectors. So if you have redundant clusters there, if you have two clusters represent the same information, and you essentially splitting the share of that percentage throughout the cohort. And in the end, if you do a regularized regression, you can just throw one of the, of course you lose a little bit of effect size, but of course that you can also visually inspect and also use other information. I will get to that.
Don't you think this is a tedious job? Visual inspection.
But you also have other statistics helping you. For example, for each cluster, you have, for example, the percentage of patients contributing tiles into it. I think the major risk for us is we're identifying clusters that are too patient specific, right? So then you lose the predictive power carrying through in the entire cohort. But I think you want some patient specificity in those clusters. That's why we listed the number of patients contributing those clusters, and also the number of tails. Again, a technical risk is that you have the number of flies contributing clusters, and etc. And a pure tail count where you have a cluster with superficial images coming from a minority in the cohort. Yes.
Okay, that's fine.
Sorry, not this part, but we have a session that
When is it due to start? Sorry. Is it due to start now? Yeah. Oh, okay. Sorry. We'll wrap up.
Okay. I'll just wrap up. So here, I'm not going to do details. These are part of the visual inspection. You can basically we have our pathologist collaborator looking through those images and helping us what they mean. But actually, you can. What we find here is that in addition to the TCGA overall survival test, we look at an independent cohort from New York University. And then we ask the question about progression-free survival. So this is where your question about independent cohort. So what we did for the independent cohort is that we project tails from those individual cohorts from clusters we identify from TCGA. Now we do the same thing, and interestingly find common clusters that are high risk in overall survival and high risk in progression-free survival. And just want to quickly
We'll leave any more questions for later because there is another session about to start. Sorry. We'll have the opportunity to spend time with most of this is our group. So
yeah. So I'll just quickly go over just a few minutes. So this is where we use HoverNet, and obviously you can annotate your clusters with HoverNet annotations. So we basically ask two questions: is this cluster overrepresented in the cell type in terms of cell number of cells per tail, or underrepresented in this case? And then by asking that question, we did a KS test. You can use the test to quantify that, and you can again generate a heat map of different clusters and their association with different cell types. And then again, we see here they are color coded in terms of their hazard ratio. Purple and red means they're more dangerous, and green means that they are more sort of okay. And then you can see there's consistency between two entirely different cohort and two different tests. Again, with the composition vector, you can associate with genomic data. So we did that with essentially transcriptome data on derived immune composition variables. I don't want to go into the details of this, but the take-home message is that the same clustering with the same tendency in terms of risk, and then they show interesting directions in how they are associated with whether it's adaptive immune response or more mutations, etc. That will be it. So finally, before we go, we are recruiting in 3 different cancer types, and if you're interested, please talk to me. Thank you very much.